Good afternoon, all. Today I am going to give a video lecture on discrete Fourier transform. So before going to discrete Fourier transform, so first of all, what is transform? So why we are using transforms? So transform can converting from time domain into frequency domain. So why we are using transform means to analyze the system response in time domain analysis is very difficult. So that's why we are analyzing the system response in frequency domain. So that's why we are using transforms. So already we know there are different types of transforms. Fourier series, Fourier transform, Laplace transform, Z transforms. So these all transforms are changing from or converting from time domain into frequency domains. Okay. So coming to discrete Fourier transform. So in many applications, the processing of signals in frequency domain, the analysis of signals, frequency, periodicity, energy, and power spectral analyzed in frequency domain. So frequency analysis of discrete time signals is usually and most conveniently performed in digital signal process. So before DFT, we are using discrete time Fourier transform. So discrete time Fourier transform we can apply for periodic signal and as well as for discrete time signals. So here in discrete time Fourier transform, so it is not convenient to perform the operations on discrete time signals. So that's why we are preferring discrete Fourier transform. So the applications of discrete Fourier transform. The first thing is spectral analysis. Next one, convolution of signals. Next one, partial differential equations, multiplication of large integers, and data compressions. So these are the applications of DFT. Next, why DFT? Mainly there are two reasons. So first one is it allows to determine the frequency content of signal. That means that is a spectral analysis. Next one, perform frequency analysis on a digital computer. So these are two reasons we are using DFT. Next, that comparison between Fourier transform and discrete Fourier transform. So Fourier transform is a function of omega and so cannot be processed by digital system. So by using DFT, we are going to convert the continuous function of omega into discrete function of omega. Next, the discrete Fourier transform is obtained by sampling the signal of the Fourier transform at finite number of frequency points. See, for the discrete time Fourier transform, the range is discrete time Fourier transform, the range is up to infinite range. So from that only we are extracting finite samples. So with discrete Fourier transform, we are going to apply for finite sequence only. Next, the sampling period range is 0 to 2 pi. We are going to sample the sequence. That is omega k is equal to 2 pi k by n. Next, coming to the definition of discrete Fourier transform. So discrete Fourier transform we are going to apply for finite sequence for discrete time signals. That is x is equal to 0, 1, 2, 3 up to n minus 1. So here we are going to consider only some finite range. That's why I'm going to consider 0 to n minus 1. Suppose in discrete time Fourier transform, that is DTFT, we are going to consider minus infinity to infinity, but in DFT, we are considered only finite range, that is 0 to n minus 1. So definition of DFT, that is DFT of x of n, that is equal to x of k, that is summation is equal to 0 to n minus 1, x of n, wn power kn or e power minus j2 pi nk by n. So here n is range from 0 to n minus 1 and k is also range from 0 to n minus 1. So here DFT you can define in terms of fiddle factor also. That is another definition is there. That is summation n is equal to 0 to n minus 1 x of n wn power kn. So here wn is called as fiddle factor. So why we are using fiddle factor means to make the computation of DFT is little bit easy and very fast. So that's why you're using fiddle factor. Next, coming to IDFT. So IDFT is a inverse discrete Fourier transform. That means it is converting from frequency domain into time domain. So here the IDFT of x of k is equal to x of n, that is 1 by n summation k is equal to n minus 1 x of k wn minus kn or e power j2 pi nk by n. So here the difference between DFT and IDFT. So in IDFT, we are adding 1 by n. Another one is e power j2 pi n. That is the difference between DFT and IDFT. So DFT converting from time domain into frequency domain. Then IDFT is converting from frequency domain into time domain. So that is the definition for DFT and IDFT. So let's see the one example for DFT. So these two definitions is also called as DFT pair. That means DFT definition and IDFT, these two definitions we called as a DFT pair. Okay, let's see the example. So find DFT for a given sequence x of n for 0 less than n less than or equal to 3, where x of 0 is equal to 1, x of 1 is equal to 2, x of 2 is equal to 3, x of 3 is equal to 4. Okay, so that is a problem. So here given data is x of n is given. So x of n is equal to x of n is equal to, sorry, x of 0 is equal to 1, x of 2 is equal to 2, x of 3 is equal to, x of 2 is equal to 3, x of 3 is equal to 4. So here number of samples n is equal to 4. That means x of n is equal to 1, 2, 3, 4. Okay, so now we are going to substitute k is also from 0 to n minus 1. So here number of samples capped n is equal to 0. So x of n we are going to consider from n is equal to 0 to 3. That means 0, 1, 2, 3. Similarly, we are going to consider k also. Here also k is range from 0 to capital n minus 1. Here capital n is equal to 4. That is 0, 1, 2, 3. Now substitute at k is equal to 0. So summation n is equal to 0 to 3 x of n e power minus j2 pi nk by n. So here k value is 0. So if k value is 0 means e power is 0. So e power is 0 means that value is equal to 1. Then summation n is equal to 0 to x of 3. That is x of 0 plus x of 1 plus x of 2 plus x of 3. So here x of 0 value 1, x of 1 value 2, x of 2 value 3, x of 3 value 4. That is 1 plus 2 plus 3 plus 4. That is 10. That is at k is equal to 0. Next, k is equal to 1. So formula x of summation n is equal to 0 to 3, x of n e power minus j2 pi nk by n. So here k value is equal to 1. Then x of 1 is equal to summation n is equal to 0 to 3 x of n e power minus j2 pi nk by n. So then x of 1 into, sorry, x substitute n is equal to 0, x of 0 into e power minus j2 pi n plus x of 1 into e power minus j2 pi 1 by 4 plus x of 2 into e power minus j2 pi into 2 by 4 plus x of 3 e power minus j2 pi 3 by 4. That is equal to 1 into e power 0 plus 2 into e power minus j pi by 2 plus 2 into e power minus j pi plus 4 into e power minus j3 pi by 2. So e power minus j pi by 2. So e power minus j pi by 2 means that is cos pi by 2 minus sin pi by 2. So here cos pi by 2 value is 0, sin pi by 2 value is 1. That is minus j. That is minus 2j. Next, minus 3 plus j4. That is equal to minus 2 plus 2j. Next, k is equal to 2. That is summation n is equal to 0 to 3 x of n e power minus j4 by n by 4. So similarly, we are going to substitute n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. Then finally, we got 1 minus 2 plus 3 minus 4, that is equal to minus 2. Next, at k is equal to 3. So x of 3, summation is equal to 0 to 3, x of n e power minus j 6 pi n by 4. So that is equal to 1 plus 2j minus 3 minus 4j into minus 2 minus j2. That is equal to minus 2 minus j2. So that is k is equal to 3. Then finally, we are going to conclude. So DFT of x of n, that is x of k is equal to 10 minus 2 plus j2 minus 2 minus 2 minus j2. So that is the example for DFT.